I'll start. Ni dah on eh? Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. We start our majlis today bi Ummul Kitab Al-Fatihah. First of all, thank you very much for those attending here at IIIT office and also those attending online through Zoom and Facebook. We are going to continue our weekly discussion hosted by IIIT Young Scholars at IIIT office. And today we are delighted to have with us, inshallah, Fadilatul Doktor Raif Rafideen, and from University College London, who went there under the auspices of the Royal Scholarship Beasiswa yang di-Pertuan Agong in 2018, and he's doing his PhD in particle physics. And the book that we shall discuss today is of paramount importance towards the discourse in modern physics and its relationship to religion and to our creed, especially in Kalam, written by contemporary scholar by the name of Professor Basil Altaie, who's currently in Yarmouk University, Jordan. He obtained his PhD in Manchester University, and the book that we are going to discuss today is God, Nature and the Cause, which is how Professor Basil explores the relationship between Kalam, or theology, or discursive theology in Islam, and its relationship to modern physics. Without further ado, Dr. Raif will discuss more about this, and we will open the discussion at the end. So any of you would like to ask questions, please send it to the comment section, or you could also ask in Zoom, those who are participating live. And without further ado, فليتفضل مشكورا. The floor is yours.
Thank you so much, everybody, for inviting me to talk about God, Nature and the Cause. So this book is written by Basil Altaie. So since we already did the introduction, so basically you can call me just Raif or Brother Raif, which one's your convenience for you. So I'm basically purely experimental background in particle physics. So I don't have much on background on theological aspects and sciences. So this will be my first book dissection that I've been read, since that I'm trying to understand like how the theological aspects in our lives could lead us to discoveries, or maybe change our perceptions upon the universe that we're seeking, and every single day. So as we know that nowadays, most of our syllabus are derived from the Western intellectuals. For example, like you can say in classical physics, we call it Isaac Newton. So if you learn in schools, especially in on the first topic of physics, you will learn what is the principle of motion. And also on other things, it gets more advanced, and predominantly like most of them are scholars from the West. So the questions that we've been asking right now is that how do these Western scholars they inspired from, and do they derive these kind of knowledges out of their own rational thoughts or some random thoughts? So there must be some built upon a theories on top of these that they develop it towards to the modern, what we call it, science or modern physics. So as a personal journey of myself, like I just started to into this philosophy and also on this Kalam. This will be my very first intellectual discussion on this kind of topics. So if I have any wrong on my facts, please correct me. And I'm trying to relate so what I've learned and trying to give some reflections of like what can we do on making the contributions from the Islam, or we can say from the aspects of theistic view towards the modern science that we've been going right now. Okay, so first of all, why I choose this book? It's quite random because initially, like Brother Hilman asked me to introduce me to a couple of books to give some discussion, but at the end, like maybe thanks to Facebook algorithms, so I found this book. So I read through of it for a couple of weeks and give some insights, and it turns out like I feel more confident to discuss a bit on this book. So it gives you more on what I've been researching for and also looking for my journey. So for the start, okay. So what is Kalam? So from this book, Kalam itself is an Arabic word. It means words. It means words. So if we put in the context of religion, or you can say theology, it means the word of God. When you say, for example, it's Kalamullah, it means that it's a word of God. So the history of Kalam is quite interesting. Like it all started when the Muslim empire started to expand from the Arabian Peninsula, and when they conquered on many other places. So when they encountered contacts with different civilizations, for example, Persia and the Greek civilization, so they tend to discover a lot of different scholars and ideas and philosophical writings by these scholars, and they were inspired for it and give it some translation to it, and then they derive their own way of developing the theory. So so much of this progress happened during Abbasid Caliphate, when these lot of Greek influences applied to these Muslim scholars. They were so much intense between those who in favor with the Greek philosophers and those who like more towards to affirming the Aqidah, or we call it the theological aspects. So on this side, like we have like divided two different groups. We call it the Mu'tazilites, and another one is we call it Al-Sunnah wal Jama'ah. You can say it's Ash'arites and Maturidites. So when this group of people, like when they have like intellectual discourse and it's pretty much like intense during this time, so they kind of like develop a way of like make it centric point of view, how to reconcile with philosophy, which is derived from the Greek, and the theological aspects that we derive from Aqidah, or you can say from Kalam point of view. Not Kalam, I mean from Ahlus Sunnah wal Jama'ah, the Quran and the Sunnah, and to make sure that it doesn't divert away from the Aqidah that we learned on. So this is how the Kalam was formed. So some claims that the Mu'tazilites is the one to introduce it first. Some say it's Ash'arites. So from this book, it says that the Mu'tazilites is introduced first, and then it developed further by the Ash'arites. So the Kalam, they have like two types. One is called the Jalil al-Kalam, and it's more like a general discourse about concerning the Kalam. And another one is called Daqiq al-Kalam. So it's more focused on a more detailed view on Kalam, on aspects on phenomenological. For example, like space, time, heat, matter, time, I already mentioned time, gas, for example, whatever like surrounding us is way more details. So that's what we call Dakik and Kalam. So the book that they discuss here, like we more focused on Dakik and Kalam, so which we focused on the detail aspects on this Kalam on physics point of view. So yeah, sure. Okay, let me. So they are basically about 3 principles of Kalam. Okay. So one is basically the idea of monotheism. So which means that must be fundamentally, the root cause of everything must be from God. In Allah, right? And then secondly is the Quran is a source of knowledge. Right. And then the third one is basically whatever causality comes to God. So meaning if you want to write in terms of flow, you can say it's like God, and then cause, and then you say this is the world that we're living in. God, cause, world. So these are the basic 3 main principles of Kalam. So from deriving these 3 different principles, that we have like the doctrines that we imply. So we have the idea of temporality of the world, which means this world is not like kind of can be, it's temporary, so it's not permanent. And we have a discreteness of natural structure. So meaning that the fundamental building block of the world, you can say universe, is built of these small, tiny objects. Or you can say something like, we call it substance, or they call it as Jauhar. Jauhar. And its relation between all of these, this Jauhar, we call it Arad. I'm not sure it's Ain or Alif. Is it Ain? Ain, yes, Ain. So it's Arad. So Jauhar and Arad is basically, it's like intertwined. So they must be exist with each other. For example, like if I have a table like this, okay, I know table is there, and this table we call it Jauhar, and the color of it, the texture of it, we call it Arad. There's like some examples that we can imply how can we relate on this Arad and Jauhar. So, but if you relate in quantum physics, like it will be more interesting. But that's the concept. So that's the discreteness of the natural structure. Like it relates to this. So and then we have continual recreation. So meaning that for every moment in time, there will be continuous new creations coming up. Doesn't matter like it will be a same state or not. For example, like I have like a time to 0 or time to 1 seconds. So in here and here, there will be like a new state. So meaning that a new creation coming up. So they say this is creation number 1, then this is creation number 2, and then so on, so on, so on. So this is how Kalam point of view like imply that they have a continual recreations of the universe. I mean, in every single moment of time, there will be new things that we created. Okay. So and then the indeterminism of the world. Okay. Indeterminate. So this thing is basically referring to that we couldn't predict an exact things in projection of the world. For example, like I expect that I will throw a stone and then the trajectory is there. But even though they can be determined, but when it comes on a bigger complex on the universe, like it's basically indeterminate. So what we can do is we only approximate. So that's why like the interdeterminism of the world came up. So meaning that what we do, we just expect things, but we not really formulate everything. We cannot determine the whole process, the whole universe, because of the complexity. So this is like, it goes back to like the way how we understand about the knowledge that we learn. When Nabi Hidr said, I think it's Surah Kahfi, if I'm not mistaken, even the whole knowledge, the ilm that we learn, right, is only like a tiny drops of water. So that is the whole knowledge that we learned in the vast oceans of the ink. So if we write it down like 7 oceans, like it won't be finished, and then you can still. Yes?
You are making statements. How are they related? I don't understand. You're not proving it.
No, I'm trying to discuss about the book. Yeah. Yes, from this book. Yeah, yeah. From here, like this is the derivation that you get.
How do you derive it?
Well, I'm not going to go that deep, but this is the what I've been understand right now. Yes.
So it should not be. It should not be statements.
So I do understand.
All of these are statements.
Yes.
One of these is a statement.
Yes.
These are statements. How they are related, I don't understand. And then all of a sudden you are talking about creation, recreation, proof. Why should I accept?
So I'm not going. I will come back to that later on. So I'm explaining this for a while. Then I come back to you. Is it okay? Okay.
You want to be convinced that these statements are true.
Yes. And I can't even see the relationship of these different statements. The world is temporal. Proof.
Yes, of course we have Qiyamah, so that's why it's temporal. Okay, I don't understand. So what context? Okay, okay, apologies for that. I'm currently new to this, so I'm trying to understand the Kalam. Pardon me if I'm wrong. So this is what I've read in the book. I'm trying to understand, but the structure from the logic behind this, I haven't discovered yet. So if you have any inputs for this, please let us know. Yes, words. Yes, Puja, yeah.
Where is the proof? You are so far making statements. And the statements also have problem in its relationship.
Okay.
There's a lot of problems.
Okay.
The world is a Jawhar or not, and then
Yes.
creation or recreation.
Yes.
It's not obvious. So where's the proof? Why should I believe what you say? Give me a reason to believe. Huh? Sorry?
I say I don't know. Like I don't know where's the connection between. Of course, like it would make sense because you want to have convincing how this get to that, right? So the thing is, like, I'm trying to just give statements what it says in the book.
The causality argument.
Yeah.
Suddenly you have approximation argument.
Yeah.
Causal relationship.
Mm-hmm.
Contradictory.
Okay. All right. I'm not expert in philosophy here, so pardon me if I couldn't answer your questions, but
If you have some insights from particular physics to these arguments.
because he wants the relation from here to here. He wants the relation to here to here.
That for each each of the statements,
Yes.
if there is some arguments or discovery in particular physics that give some backing.
Well, temporality of the world, of course, like you have a quantum states that is changing over time. So that states then won't be stick, that it will change over time. Yes. That's the context.
Just because it changes doesn't mean it's not permanent. Doesn't mean
Yes.
it's temporary.
Maybe I can add in terms of the principles of superposition, if we are speaking about
Yeah.
quantum physics,
Yeah.
which means when you observe, it changes. So
Yes.
the temporality of the world, which means in whatever state it was, it will change when you observe.
Yes.
Which means it never permanent.
Yes. But I just don't understand how to correlate with his questions on.
I think temporality is hadith here,
Yeah.
which means it's new.
It is new.
Yeah.
But the concept of new, the world can be eternal. It was assumed the world was eternal. If you follow Aristotle,
So, yeah. Yes.
yeah, co-eternal. God is eternal, all is eternal. Now, they argue that the world is created.
Mm-hmm.
You need an argument. You cannot, as Kalam, as a Kalam, argue just with statements. It must have a future. It's a controversial statement.
So anyone want to add up?
Just because someone says, then
So anyone want to add up?
You just have to show a point.
the whole idea of Kalam is causality need to be proven. Who said there must be causality?
Yes.
Ghazali rejects causality. So, necessary.
Okay. So you want me to continue or?
Continue.
Continue. Right. Thank you.
Have some.
Let's see if you prove it.
Okay. And also mention the integrity of space-time. And time. So, which means that space and time itself existed at the same time when universe was created. So that was the one of the doctrines. So, okay, you already mentioned about Johar. Of course. Okay, that is what I understand about doctrines of Kalam. So now I'm going to on modern physics. So we can start off with Newtonian.
Yeah, right, figure.
Is it too small for you?
Yeah.
Yeah. Okay. Okay. All right. All right. Okay. Right. Okay. So Newtonian physics is basically we're dealing with deterministic systems. For example, when you have a force, or you can say 3 Newton laws. Okay, law of motion. So whatever you push, there was opposite. Yes, every action there must be reaction, and then every force is basically to push it based on the mass on this, and then you will get the acceleration. And at the same time, everything must be moved in a constant speed unless there's something to stop it, which is that it's inertia. Okay. So Newton is basically built upon where the space is absolute and time is also absolute. And also like the laws, not laws, I mean the physics are basically deterministic. So you can do this by projecting some variables. For example, I have like force here, and then I have acceleration here, and then whatever the inclinations, or you can say gradient here, is basically is how hard it is to push an object. So that can be correlates to the mass, for example. Yes, F equals ma, right? Okay. So Newtonian physics like developed kind of a lot of progress in terms of like making machinery, mechanical motions. So on the late around 1700s, so you have this we call Lagrange. I can't remember his full name. So Lagrange basically developed where a system that is more complex that involved with multi-body objects. So they developed this, we call it Euler-Lagrange equations. So for example, if you have like a pendulum, so you can derive using Newton's law of motion by just deriving all these forces that are acting on this object as long as they equal to each other, and then you can get what are the acceleration, the change of angles, and so on. But when you're dealing with like multi-body systems, for example, a double pendulum, like that, for example, you would expect that you get you need more complex equations to derive it. So Euler-Lagrange equations basically can solve most of these trajectories and implement it into these multi-body systems in a more nicer way and quite a bit accurate. So it's still deterministic. No. Yeah. No, this is push. But the case of Euler-Lagrange equations, like the whole system is a closed system. Yes.
To begin with a push. External.
Okay.
To move, something needs to push to move.
Mm-hmm.
It's not internal, it's not desire to move.
Okay. External.
So how to explain first?
External. Of course, and then, for example, pendulum persons like lifted and then released it. Yes.
But why did the person do it? His assumption is Newton's physics is contrary to Aristotle's
Mm-hmm.
desire to change.
Okay.
Things change because they desire to change.
Mm-hmm.
It's internal. This is external.
Okay.
So the movement from internal to external. Explain.
I don't understand.
Are you referring to potential?
Yes. Look. There is you see everything else as dead. It needs an external force to cause it to move or change.
Okay.
Aristotle did not argue that way.
Mm-hmm.
It argues that all things desire to change.
Okay.
So what changed from Aristotle's physics to Newton's physics? And how did you reject this idea of everything as external force causing everything else? It's not internal. The internal is that you people there
Yes.
pendulum and let it go.
Uh-huh. Okay.
The pendulum moved because of your push. That's external.
Okay.
So how do you explain the Newton's physics as opposed to Aristotle's physics?
What is Aristotle's in this case?
No, you changed that. Yesterday you were different.
Yes,
So why didn't you come different?
based on that.
That is internal change. That's external change.
Okay.
What happened? Why your body reacts this way is that external.
Change.
But why your body desires to react this way is internal.
Okay.
So your explanation of Newton
Mm-hmm.
is very external.
Okay.
Because there is no forces, no forces. So how do you explain?
I don't understand.
Suppose why
Why do things change? Rather than how do they change?
Okay. Okay, this is my understanding. I don't know if we quite answer your questions. So I have like a system is already running. For example, I have like a maybe moving objects around, and then I apply to it, the system do change.
Yes, but the initial start
Okay, the initial start.
is external.
Okay,
If you have a pendulum that continuously will never stop,
running. Mm-hmm. Okay.
that's an external force. Why did he do it? How did he do it? You're acting as if man is a machine. Not a machine. Newton's physics argues for external world is machine. And go on.
Okay, I'm really confused. Like, what is the context here? Because I'm a physicist. Like, I don't understand about much philosophy. So this is my first start. So pardon me if I don't have any much background on philosophy. So if I'm wrong or maybe it doesn't answer any questions, so enlighten me in the part.
Science,
Yes.
not a science. Philosophy science.
Yeah. So
Scientific history.
yes.
You will see the movement of how people develop. Another
Okay.
is not obvious.
suppose once human beings start to see themselves as distinct from this world, then they start to treat the world as mechanical, including themselves. And so the shift from internal to external changes happen.
Man acts. Everything else reacts. Everything else reacts and it's predictable how the reaction is. But man acts. Whether he chooses to act or not to choose to act, that's internal. You get it?
Okay.
Your car has no choice. But whether I press the pedal or not, I have a choice. But once I press the pedal, the car will it reacts.
Mm-hmm.
So your system, your Newtonian system, doesn't explain who acts. It explains the reaction.
Okay.
How do you create the action?
By applying the external factor.
There must be purpose. Or it's not as reaction. The Newtonian physics treats everything as a machine.
Mm-hmm.
the Aristotelian one does not read everything as a wish.
Okay.
And we also can see that when given in Newtonian physics, it does not explain the beginning part. It explains everything else. The reaction. It doesn't explain the act.
The purpose of the act.
Oh, why?
You mean the purpose of the act? Oh, okay.
The external is there.
Mm-hmm.
Everything else that happens. Your fidelity is sure. But I don't get it. What is it?
No, I'm trying to explain on my presentation here, and then just things came up like just don't get it, the causal relation. Yes, I'm standing in the house. Yes.
But the beginning is action.
Yeah.
This the rest is of the reaction. Without explaining the action, that whatever we know. It's a big explanation. Why did you begin?
No why. So you're saying that Newtonian physics doesn't say why. So that's your conclusion. Okay.
That's not. It solves the how. It doesn't solve the why.
Let's see. Newtonian physics.
I'm not sure though, but he did mention about the changes to quantum, something like that.
Go on. Sorry.
No, it's fine. Right. So Euler-Lagrange basically developed more like a more complex system where you involve with many variables that you can formulate using these equations. So how interestingly, like when these Euler-Lagrange equations basically can be applied into more sophisticated system, like for example in quantum theory. So let's go to quantum. Okay, it all started when we trying to understand is light a particle or a wave. So when we look at from Newtonian perspective, so light is basically is a wave. So it turns out that when we go in quantum, light is basically is also has momentum. So that's why it can be act as a particle. So when we have this duality of a wave and a particle, we tend to formulate like how this particle can have energies. I mean the light have an energy. So Max Planck derived this energy of these particles is just basically h, and it's the frequency that. So to the extent de Broglie further developed when the particle has a momentum. So the momentum itself is just h over the wavelength of the particle. So the longer the wavelength, the smaller the momentum is. So the higher the wave, the smaller the wavelength, the higher the momentum is. So it correlates to the frequencies. So apparently Einstein postulated that the particle is a wave and a light. So because that they behave a wave, and also they have a momentum. So that's where you can see how the quantum starts. So, 1 second. But we try to explain on these concepts, particle and the light. So we can apply this basically on electrons. So when they fired electrons on the double slit experiment, the electrons also behave like a wave. So when you look at the screen, and then this is the source of electrons. So it turns out that the electrons behave like interference. So when you look at the screen, you will expect like some fringes that on the screen. Screen. So, yes? Okay, so basically electrons also has a wave particle duality. So this is where like we see that the quantum nature of particles. So meaning that when they behave like a wave, so meaning that they kind of will have some probabilistic. So what they're trying to interpret is like this quantum theory. Max Planck, no, not Max Planck. What's his name? Heisenberg, yes. So Heisenberg deduced that the uncertainties of finding this momentum and the position is basically not greater than this Planck's constant. So the moment that you're trying to measure precisely, you don't know like how accurate you are on measuring the size or maybe the location of the particle itself. So it won't be very certain like you find either these two variables. Same goes to like if you want to find like the measurement of energy, and even at the time that where the particle is, it also has the same uncertainties on these calculations. So that's pretty much in quantum. So from this point, Schrodinger's like proposed like you can some sort of predict the trajectory of the particles by using the we call it Schrodinger equations. So what they do is like the particles, right, can be denoted as psi. So it does move in space and also in time. So this behavior of the wave function of the particles can be derived using Schrodinger. So we have from kinetic energy of the part, and then you have potential energy in the part. And then from this point, you basically changing on this, it depends on the changing of the whole system. Sorry, is it Hamilton? Okay. So when Schrodinger introduced this, it works perfectly on modeling atoms and even like the orbiting of electrons. But how electron orbits around the proton was developed by Bohr, and when they incorporated with the Schrodinger's equations, they found that like they have so many different variations of types of wave functions. So instead of like you're orbiting around electron there, so the electron have like certain structure, we call it the cloud probabilities, because of the Schrodinger equations. They have a different energy states. So meaning that if I plot these electrons here, so let's say this is like energy state 1, say value, let's say 1 here. So because of the quantizations of these electrons on these every energy levels, so they tend to have like instead of one energy levels, it can be like infinite until that it breaks beyond, we call it ionization potential. So that's the Bohr model of the atoms. So how interesting the thing is like because it behaves wave and particle, it also becomes a discrete. So it doesn't behave like a Newton, more like individual itself, even though it's probabilistic. But Einstein, he suggests that despite of these probabilistic and also discrete, it can be represented by like a statistics. We call it statistical physics. So you can have like a probably, for example, I have like a type of functions like that. So these are basically where the location of these particles, the probabilities, right? So when I integrate of these, all of them, I know that I will get pretty much like all probabilities combined, and I will find where the places are as long as it's within these boundaries. But the thing is, if you want to find the exact point, you will know that how much probability would you get to find that particle here. So when you incorporate with statistics, you just multiply by with the number of particles that is associated in that system. You will know that how many particles would be there in that place, for example. But if this is position and this is the probability, that will be it. So that's how we incorporated on measuring things. And even until now in particle physics, like we use statistics to find the probabilities, like where most of these particles are. So what they do is like they incorporated these wave functions by, if you learn calculus, it's like just integral, or you can just sum all of these wave functions, and then you take the conjugate of it, and then pretty much like you got the whole thing equals to 1. Okay. So that's the nature part of this quantum. So all of these basically comes from the definition called Copenhagen interpretation. Yeah. So whatever like we using now, most of that is the Copenhagen interpretation. Yes.
I'm a student of physics, so I want to relate this. I don't need to.
Yes.
Actually, what is the electron? Is it a particle or wave?
From what we define now, because of this behavior of the interference patterns, and also they will also have momentum. So basically, they are both. Yes. If you want to formulate things, for example, the wave, the context. Let's say if we look at electrons, we use the context to find the probabilities or the particle where it lies. So that's the wave nature. That makes that we're going to count, expect where the locations are. So we use that because wave have patterns, right? So when we apply that mathematical formulas on the wave patterns, we will get certain values. So we call it expected values. So let's say you want to incorporate it with energy. So what is the expected value of the energy of the particle, of electron? So you use that wave function here. Let's say my wave function is like this. But if you constrain them into like a system, or maybe like a box, for example, you would find like there are probabilities of electron maybe around here, maybe like, let's say 50%, maybe here it's nothing, maybe here's 50%, for example, like that. So we use the wave to find the probabilities, mostly. But we also can use it to find the momentum as well. There's correlation between.
I think my question is more basic. What is wave?
Wave is a propagation of energy towards the space.
It's the propagation of energy.
Yeah. In the space, yeah. Also in time as well. Okay, how we define particle, it should be have mass. But the thing is that even the light doesn't have mass, it's particle. So that's contradictory, right? But as long as you have momentum, we call it as particle.
With
Yes. Can be particle. But in terms of quantum, we explain in the context of quantized objects. But if you consider, like, for example, a huge ocean of waves, right? You don't interpret that into the context of wave particle duality, because that is more like classical physics. So you follow Newtonian, or you can use Navier-Stokes equations to derive it. But when we deal in quantum, we have a different system. The way how we define things, like we define a particle can be a wave and a particle in the context of this. But if you go in a microscopic scale, for example, like I said, ocean or maybe lake, you use Newtonian. So you cannot use that definition for that. So you follow the standard momentum way of how to calculate. But if you go into quantum, that's where you define this duality. Yes. So that's the quantum part. Any questions? I want to go to the relativity part. Okay, all right.
Is this as an explanation of one of the pillars there?
So I will go to that soon after this. So I'm trying to explain a bit on the quantum part and then some relativity, and then I go to here. Yeah. So so right now, so this is pretty much of like the foundation on the quantum, how we built. Doesn't matter condensed matter physics, particle physics, even what else? Astrophysics. Even like we did involve on this, but all of these are basically this foundation on quantum theory, like how we advance further into like develop more complex system. No, it's not Newton. No. It's another school, yeah. So it derived basically when they observe this kind of phenomenon, like the fringes, and then they observe that they have momentum. So that's why they derive this kind of equations. So how can you find momentum of the photons, or you can say light? So you use this equation. So you postulate that it relates to the wavelength of the particle. I mean, wavelength of the wave of the light. Sorry. So that's pretty much building blocks of quantum Copenhagen interpretation. Sorry. So, any questions? Okay. All right. So that's pretty much quantum. Let's go on. Can I? What is? Okay. So let's go to relativity. So this is another very important subject when you learn physics. So, okay, the idea of relativity actually starts back during Galileo. So when you move and your friend's moving as well, but when your friend is moving faster than you, right? Your relation velocity between these two, for you and your friend, is basically the differences on that. So your friend, if you're moving and also your friend is moving faster, you will not see your friend that is moving that much, that fast, because like you also is moving. So that's how Galileo like introduced the relativity. But when it comes on Einstein has like another postulate. This is Galileo. So let's say this is V1, this is V2. So the difference between your 1 and 2 is just 1. That minus that, you get it. For example, this guy is moving 10 and this guy is moving 5. So you, number 1, see these two, apparently it's just 5. Contoh lah. For example, this is MH. So you won't see that your friend's moving 5 kilometers per hour faster than you rather than taking. So that's Galilean. So it's pretty much logical sense. Even like if you drive a car and then your next car is moving faster than you can see that it's not moving faster to your frame of reference. But if you're stationary, you will see that it's moving fast. Okay, contrary to the Einstein, Einstein has like a different postulates. So what he says that speed of light is constant. That's one. The second thing is nothing can go beyond the speed of light. Especially particle with a mass. So we can say more like massive particles. Okay. So from this postulate, Einstein deduced that your time, the frame of reference, for example, I have like train moving, right? Let's say train is moving that way. And I'm looking at here. Okay. So I have my own set of clock. So my clock is based on the reflections of time, reflections of light. Okay. So I have like two mirrors here. Okay. So I start with bounce one and goes back down. So that's my clock. Let's say I clock one. And then there's another clock here, right? And then there's another person here, right? Also moving the same way. Okay. So what happened here is like, because of the speed of light is constant, so when I see this guy is moving, right, the path of time, basically the light travels longer, in my point of view, on this train. So let's say this is when it's moving. I would expect that my time will be looked at that. So for example, like I have like a two mirror here, and then when I'm moving, you would expect that there will be some trajectories on longer path of the light according to your frame. But my frame, I'm still looking at ups and downs. So because of these, they figure out that they found that the time on this person, let's say this time 2, this is person number 1. Okay, there's a time dilations going on this person. So this can be derived. Let's say this person here 2 is just that. Okay, this is the velocity of this train. Okay, and that is basically the speed of light. Okay, so if you push the speed of light, like you in your frame, when you see this person, like it will be infinite, meaning that it's kind of like you look, this guy is frozen, some sort of that. But from person look at you, it says like, oh, I think this guy is already old, some sort of that. So that's why like this is where how they derive the time dilation. Interstellar is different case. This is special relativity. Oh, sorry, I have another two.
By the way, again, these two postulates where Einstein is claims, right?
Yes, it
was proven through
formula and also from Michelson interferometer as well. Yeah.
So when he said nothing can go beyond the speed of light,
meaning the mass safe particle.
so it's impossible, or
According to postulate, yes. Basically, like if particle has a mass, cannot go to beyond speed of light. If particle has no mass, it can go beyond speed of light. Not beyond, I mean like it can go to speed of light. If you go beyond the speed of light, there's a different story. There's a different story, like it's more complex. So yes, so this is how time dilation comes in. But it also not just time dilation, but it can also contract the length as well. So when you have this kind of effect, this thing is what we call Lorentz factor. Okay, so when this thing influences the time, so one of your references, you will see that you are aging much longer. So for the length, this is the other way around. you would see that this guy, instead of stretch, but you will compress like that because of the fact of the gamma factor. So the formula is just flipped. So length 2, length 1, like that. Okay, so that's the special relativity part. Sorry. And from this point, they derive the famous equation E equals to mc squared. So it relates with the four momentum. It's much more complex. But from these aspects, got that. Yeah. Okay. So that's special relativity. So the last bit is the general relativity. So general relativity, like it deals with the space and time can be curved. So as long as you have then an object or energy that implies in that space-time, some region of space-time, the space-time can be bent. The stronger the energy is, the higher energy is, like the stronger the time. I mean, the stronger the curved space-time. So that's general relativity. So it can be derived into black holes. Even you can models on expansion of universe, even on other things as well. So okay, that's pretty much of modern physics, right? So okay, what I find it interesting about the idea of this on the modern physics is because when they mention about the temporality of the world, it did relates to the case at where like we did have a model where the universe can be destroyed, where like we have, based on our current model, our model is basically from the Big Bang. We start from a single singularity point and with infinite density or maybe certain very high density, and then it just expand by inflation, and then suddenly like you have this whole bunch of stars, galaxies, and also particles that made during the process. And then when you reach to a certain state, when we call it dark energy couldn't resist the gravitational energy, it contracts and then it becomes like a big crunch. So that's why like I'm interested like how like Kalam like get some ideas like on the temporality of the world. Ultimate fate universe, but that depends on the certain ultimate state of universe.
You mean like
According to their own, but that would based on current measurements, it would take maybe another trillion years, I guess. But yeah, not collision, it's more like interaction. So let's say I have sorry, okay, this is observer universe, right? Okay, so they were expanding, all right, so it's pushing outwards. Okay, so what happened here is that I have galaxies around, right? This is observable universe.
in the vacuum?
Not necessarily vacuum. This is where we see from the light that we see from the sky. So the furthest light, that is the observable universe. So if you look at, we call W map. So it basically measures the time that where the universe is about 380,000 years old. That's how backward it is. So we use this time on the based on the model, then we get the observable universe, and then that's how far it is, about 98 billion years, light years. Yeah. So when all of these galaxies, right? When we have a model where the dark energy, let's say dark energy here, is less than the matter energy, which is the gravity from these galaxies, if it gets stronger, it contracts until to the point that where it crunches. Yeah. So that's a big crunch. But if the dark energy is too strong, it becomes a big rip, meaning that the space-time is ripped apart, something like that. It's not space-time ripped apart. The space-time is expanding, but the matter is ripped apart.
now the dark energy is going to be the energy lah.
Yes, that's why they expands like a steady state rather than too fast, too slow. No, it's just like fixed velocities, yeah, on this part.
Dark matter and also matter is that is what it is, right?
Yes. The galaxies, what you see, dark matter, everything that is as matter, because dark matter has gravity, but it doesn't interact with particles. Where it interacts gravity, that's weird. But from this, if the matter energy, or we can say gravitational energy from the matter, is strong enough, it will contract the universe and then becomes Big Crunch. Yeah. So this can be explained from the Einstein equation, which is the general relativity concepts on that point. So that's why, like, I'm very interested on why, like, temporality of the world in Kalam mentions about this, and some sort of like it has some ideas on where the universe could be. This is my point of view. And the discreteness of the natural structure is because like it relates back to the quantum that what I've learned in universities, and even during my research, like how does it know that the natural structure has discrete? Because when we learn the smallest things that can be logically explained from the law of physics is the scale of, we call it the Planck length. It's the smallest scale that where all the physics can be still make sense within the context of the things that we've learned. So that is the smallest scale that we can have. So Planck length, you can imagine that you yourself comparing with the observable universe. That's how small it is. So you yourself is an observable universe, and then Planck length is you. Using axioms can, but we always want to see the phenomenological aspects on it. Like, can we observe? Like, can we make sense of it? But because when you go in Planck length, the small scale of where the physics lies, the physics here, it gets really interesting, because when around this scale, the gravity and all other fundamental forces, including all of these quantum effects, it becomes really bizarre that where like you will have like maybe a micro wormholes here. Micro wormholes, and some people like introduce string theory, like you can form, there's a lot of things. Maybe like there's another hidden dimensions around, is because it's like curved into like one single length, and you have so many other dimensions around, like can be up to like 11 dimensions. So that's how like interesting things about this scale. And this is the scale at where the lowest we can go to make sense the physics that we understand now. So that's why like this thing intrigues me, like why this case. That's why like I'm trying to explore. And continuous recreations, another thing that I do interested, because if you look in the concept of virtual particles in quantum physics, so I'm basically from particle physics background. So whatever interactions in the particles, we have this called vacuum polarizations. So when these two particles interacts, right, there will be like intermediary particles that just pop up out of the system that causes the interaction. We don't know why, but when we implemented that formula and then we make it into the model and then we observe it, it kind of fit with the statistically. So that's why like it just pop up our system nowhere. It's similar to like kind of like continual recreations. That's why like I'm very fascinating like how he came up with this idea. And also like the interdeterminism of the world like explains like the randomness of the quantum world and why like, everything is probabilistic. And apparently from this, it becomes a macroscopic world that you can even see that it's consistent. But when you go in quantum, like it's not consistent. When we go in the macroscopic world, like it turns out to be like it's very consistent to a certain point. So that's why like this is why like I'm interested with the Kalam. So that's the main reason like I'm trying to look into this. Pardon me if I couldn't explain a lot of reasonings on your questions, why Newtons and that, because I'm really new to philosophy here. So this is my motivation. So all of this, what I've learned from physics, I'm just trying to see which one I can start. So if you have like any inputs or any suggestions, like kindly like please like share to me, like could like explore more. So that's pretty much from me right now. Any questions?
You say that? No.
I think it's better. Because
I think I'm confused. What are you trying to prove with this conversation?
I'm not trying to prove anything. I'm just trying to relate this and what I've learned.
I can understand the model.
Mm-hmm.
There's a lot of complicated calculations.
Okay.
How is the method that what is it that you're trying to do?
I'm trying to prove like, okay, my point of view is like, is there a theory on the perspective from Kalam that you can formulate to make it the progression of modern physics? So that's the starting point. So when I look at this, like I see that these ideas like have some common in modern physics. So that's why like I'm trying to see that where Kalam can, you know, go beyond modern physics, especially when trying to make it better. Maybe they have a better model that we can even observe in nature.
Look, Kalam model. What's the proof? The absolute control, not absolute. So everything is temporal.
Mm-hmm.
And it's created, having created, therefore it's indeterminable. It's unpredictable.
Yeah.
That's what you want to prove. What you want to prove, I'm not clear.
My proof.
What you want to prove?
Okay,
What is it that you're
I'm trying to expecting like how far like it can model
model what?
the current modern physics.
Which is you're going through many different ideas.
Yes.
Which one is it? What are you trying to model here?
Basically,
Creation, recreation, or from something to nothing to something.
okay, all of these five, it includes a lot of
Branches in physics. So because of temporality of the world, it does relate with the cosmology. The discreteness of the natural structure relates back to the quantum theory. Continual recreation, it does relate to quantum theory because it involves with particle physics as well. That when we try to formulate, when you put virtual particles that just pop out of resistance, it gives them ideas. So the main thing that I want to see here is like, how can we use Kalam to develop physics? That's it.
Two different purposes. Totally different purposes.
According to
Well, something pops out. Nothing to something to nothing.
Yeah.
You're accepting that nothing can come out something.
Yeah.
And from something comes out nothing. Explanation.
we don't know what's the explanation, but it just fit with the model.
That's what the physicists observe, and they try to derive formula for it.
Observe. I don't think you can observe it.
But you can use it from models and you see the outcomes from the senses.
Some inference.
Yes.
You make an inference that from nothing can come something, and then something becomes nothing, becomes something.
Yes.
Where's your matter? Everything is either matter or not matter.
well, this is where it gives the results.
Sorry?
It gives the results. And it just fits with the model.
Inferences, just because it fits with the model, doesn't mean the inference is correct.
What we do is like hypothesis testing.
Constructively, it's consistent.
No. You cannot make the model change inferences You cannot use exception to become rule, rule becomes exception. I guess because of, you're inferring a lot of things.
Yes, but at the end, you apply axioms, and then you apply hypothesis, and then you test it, and then the result came.
You're assuming they are axioms, they are principles, they are. These are derivative.
Okay.
Doesn't prove anything. Just because you use the word axiom doesn't mean axiom even exists.
But you're consistent with observations.
A lot of things can be consistent but explained differently.
Okay.
So just because you make one assumption, this is the cause. It's not necessarily true. You're making an assumption from something comes nothing, nothing comes something.
Yeah.
That's physics.
Yes, that's what modern physics now.
Okay, fine.
Anyway,
It's bizarre for me, but
but if you have alternatives, what would be your suggestion? Is Kalam fixed with this, or shouldn't be discussed about this?
no, Kalam tries to answer different questions. As Kalam tries to answer that the world is not infinite because it's challenging Aristotle's argument for eternity of the world.
It's challenging the Mu'tazilah, right?
No, not Mu'tazila. It's Aristotle.
Al-Farabi.
The
Ibn Sina.
Muslim philosophers argue since God doesn't create in time. God, what He wants happens. Therefore, when there is God, there is world. It's immediate. Unlike you need your salary before you can go buy a new shirt. God doesn't need to wait for his salary to create the world. He wants the world is created. Therefore, it's not time difference, but intention, immediate. In other words, there is no time before the world is created because the world changes, God does not change. Therefore, there is no time, according to Kalam. Right? So I don't see how Kalam tries to prove certain things. It's not trying to prove.
But maybe that is the problem of technology, I think. That currently we have far superior technology that a previous Kalam cannot think, cannot grasp what this physicist trying to say. Maybe we have a new Kalam, I think. The modern Kalam.
You are trying to probably read into Kalam what
Too much.
never was intended.
Okay. Maybe that's true. If that
Now, if you start arguing the creation, destruction, that was supposed to be the argument that nothing is permanent, only God is permanent. And the recreation is rejecting the deterministic. But it's also proven to be, many other mutakalimun argue this is also a waste of time. God does not recreate it. It would be no function. But some argue yes. So you're trying to read into it. Probably, I think what you need to do is at least, if you want to do this, understand the history of Kalam. Why did he do it? How the differences are. Also understand the pre-Socratic metaphysics, because it talks about the changes. Newton doesn't come out in a vacuum. None of these ideas actually come out in a vacuum. But your assumption that certain things are just axioms, I find it very difficult to just simply accept. Just because you have a number of random whatever, and you make these inferences, they cannot necessarily be correct. You should at least evaluate. Your Newton never argued that something can come out of nothing. It's all it's all change. Yes. But from something to something. Yeah. Not from nothing to something.
The philosophers argue for something by using logic. I think physicists argue for something by using the logics of numbers. It's a formula.
It's not about the numbers. You see, you make it infinite just because you ate this lunch just now. Now it's full. You are no longer hungry. You assume as an inference. Now, whether this is actual inference, there are many reasons why you're no longer hungry. Maybe you're entertained by this talk and suddenly you're no longer hungry. Or let's put it, you're more confused by this talk and so no longer hungry. At least so. Okay. But the inferences can be multiple just because you assume this is one inference. And it's just because it seems to happen to you many times, it's not necessarily true.
This is what gave us modernity now.
I don't think the steam engine was based on this suddenly from nothing to something else, right? So the steam engine gives you modernity, which is very boring, very mechanical.
So do you believe that something cannot come from nothing?
That's assumption.
That's an assumption too.
The world comes from God, therefore from something. If not from nothing, then God can come from nothing.
God is an exception.
Your argument, if nothing can come something, it doesn't have to be God.
God facilitates.
But how do you explain that nothing comes something? Where was that nothing before it became something?
We have this term we call radiative questions.
Yes, which means
So, okay,
I need to wipe. Can I wipe this?
Yes.
All right. It's from mathematical formula, apparently. So we have this called perturbation theory. So let's say this is what you observe, right? And this is the real value. Okay. Let's look at Higgs boson mass. It says this is the mass of Higgs boson. Okay. Anyone know Higgs boson? Okay lah, mass of electron. Okay. So we call it bare mass electron. So this is what we observe in the laboratory. And this is the theoretical, our model, right? So the difference between these, right, comes from when we add up changes. We call it perturbation. Yeah, perturbation. So you add like some corrections on the value of the model. Okay, let's say the bare mass of electron, the mod that predicts by model, let's say 10, and that turns out that 11 here. So we add this 1 to fill in that. And this thing, the way how we add up comes from nothing.
nothing is not nothing. You just created nothing from nothing.
Yeah.
That doesn't explain why it's true.
But it works.
That's because it doesn't.
Okay, the mechanism behind perturbations, like you can explain in terms of Feynman diagrams. So let's say I have like electron here. This is not directions, right? This is more like just diagrams. So the way how you add this is because there's a vacuum in the middle of this, in the middle of space, because of this vacuum energy pops the these virtual particles here. And that is this one. This is the one that adds the mass of the electron, for example. So this thing comes out from the vacuum energy. So the vacuum energy itself, it makes into a certain mass of particles and it contributes to this. So that's the postulate actually. Yeah, but vacuum energy, turns out it's not nothing.
It's some matter in the
Super small, like I think 10 to the minus 24 joules per kilogram, I think. Okay, yeah, small, yeah. So this vacuum energy is more than enough to create like a small mass that adds the mass, something like that.
So it's not really nothing.
In a way, so nothingness means it's just like very small energy. Yeah, super something like insignificant.
But you know, if you have mass of electron and then you know bare mass of electron, and you give this to a mutakallim, probably they would come up with a different theory instead of perturbation, probably something else.
Yeah. So this is what we're doing.
Defend God or prove God. That is his key. It's not proving the world. You are the opposite. Right? You are doing from the world, you're trying to prove whether how God creates, how everything begins. They are trying to do the opposite.
So you're trying to prove God.
It depends of God or proving of God. So the argument was, why is the world temporal? The argument was God will decide whenever he wants to create. So will. For Ghazali is will. God can decide today, tomorrow, whatever day. But Farabi argues the opposite. Why does God change his mind? He said God doesn't change his mind, therefore he decides to create the world exists. That's it. Right? So there's no such thing as empty time for Farabi. For Ghazali, why not? His will, power and will. For Farabi is different. So that's how the argument for temporal works. But for Aristotle, there is no temporal world. The world is eternal. Because God and the world are co-eternal. And each have a desire. Why the world changes, it desires to be God. Since it's imperfect, it tries to perfect itself. And that's why movement occurs. Motion, change is internal. You argue for external. Push. This one is actually desire. That's the difference between for Aristotle, everything has a desire, the world has a desire, it tries to perfect itself. Human beings become adults as they try to perfect themselves. Oh, that's very different. It's internal, not external. Of course, you need the food, whatever, etc. That's external. So how Newton doesn't explain the internal part.
So you only explain the external.
Yes, the external is always the deterministic push. Therefore, the action reaction. If you just simply explain the reaction and not the action, what caused the first cause, it's very problematic. Like your Big Bang theory actually only explains the reaction, doesn't explain why it happened at that particular time. or where the first initial method came from. He doesn't argue for that. It's always T plus 1.
Not T,
What do you call it? T, is it?
not T equals 0.
Yeah, I forget the terminologies, but okay, yeah, fine. But it always after the fact, not before the fact. Right? So it's interesting idea. I okay lah, fine. You want to relate it, but as I said, you need to understand the motivation of the mutakallimun, also the history of the mutakallimun. Creation of the world is a big issue. It is a big issue. And then, of course, the deterministic also is a big issue because of the problem of evil. Is also a big issue. Interesting. My son was trying to explain this to me. I disagree with him. So. This idea that something can, nothing can come into something and then become nothing again, difficult to accept.
Yeah, that's pretty much
Is there any
it.
questions?
Right.
Fine. Question?
Yeah.
Oh.
Banyak proses lah.
Ah.
Banyak proses lah.
Alright. So, ada question dia ni, mana? Yeah. Okay, so would you like to wrap up?
Yeah, I think that's pretty much it.
Yeah, probably want to reiterate some of the points.
Yeah, I
the
mean,
last time.
the points here is basically I'm trying to relate what Kalam can provide models on physics, which maybe contradict what the Kalam's purpose is. Pardon me if it's wrong, but that was the motivation on this talk. Like I'm trying to relate on modern physics and what Kalams can correlate between them. That's pretty much of it.
Thank
Yeah.
you very much, Raif, Rafideen, for the presentation. And,
you.
I think we learned a lot. But just to make sure that you don't feel, uncomfortable, because this is the discussion that we like to
Okay,
have
you're
all the
right.
time. We learn from the sometimes he already know, but he just wants to get the discussion and debate. It's a good discussion nonetheless. Thank you everyone for Facebook and Zoom. Hope to see you next week, inshallah, on Thursday. Yeah, that's on Thursday, yeah.
Thursday.
Thursday.
Friday we have something. So inshallah on Thursday, thank you again. Assalamualaikum warahmatullahi wabarakatuh.
Salam.